So this is going to be the third classroom video if I'm not mistaken. We've already gone through igneous and sedimentary rocks, so I think it makes sense to go through the third major category of rock at this point, which is metamorphic. I will be glancing over here repeatedly because I could not print the usual lesson plan / script that I usually use for these videos, and so I kind of have to have them pulled up as well on here. So it's kind of like a double-sided situation where on one half of the screen it's the lesson plan and on the other half it's the PowerPoint, so I know like which slide we're on as you like the editor follows along for you guys to see. So yeah, I apologize for that for those of you who don't like videos where the person keeps looking away from the camera. So yeah, also my hair is a mess and I am mostly in PJs. You know, it's a lazy day. Well, lazy is one way to put it. I've been busy all day, but you know what I mean. Anyway, aside from all of that unnecessary rambling at the beginning, let's just get right into it. So today we're going to be talking about metamorphic rocks, like I said. I'm just going to show you guys again the simple, well, not again, like a new rock diagram of the three different types. I think I explained it in the last video, and probably in several videos at this point, where like igneous and sedimentary rocks can become metamorphic, but also other metamorphic rocks can also become metamorphic. That's going to be basically on slide 3. Slide 4, actually. Slide 4 is the diagram itself. But first, let's go through my actual lesson plan for the day. I'm just going to go through the how of metamorphic rocks. So yeah, anyways, we're going to start with slide 2, actually, not slide 4. Let's walk through it instead of getting ahead of myself. So like I said before, I'm going to go through the how of metamorphic rocks, like the protolith, which is just another word for the parent rock, which is the rock that it originally was before it was metamorphosed, because that has a lot to do with how it turns out after metamorphosis. Metamorphism, not metamorphosis, we're not talking about butterflies. Then the agents of metamorphism, like, which are just heat and pressure and any combination of. And the processes of metamorphism, like regional, contact, dynamic, etc. You guys probably don't know what I'm talking about when I say that. Don't worry, I'm going to walk you through it. You'll know at the end. And then I'm also going to go through metamorphic grades, texture, which has to do with foliation or not like non-foliation. And of course, grain size, hardness, all that other extra stuff that goes into how we ID metamorphic rocks. And then, you know, a few identification charts, because there are quite a few for metamorphic rocks. There's probably more than one for every kind of rock, but usually you can find the same information on any chart for like the different types, except that's actually a lie. Never mind. Forget that I said that. Anyway, the point is that there's a lot of like different charts that you can use for IDing metamorphic rocks. So I'm going to show you guys just a few that I found. And now we're moving on to slide 3. The necessary reminder, obviously, is that igneous rocks are formed from, because like, I just want you guys to remember, so I'm going to remind you every time we talk about different types of rocks, like, if you need the reminder. If not, you can just tell me to stop reminding you. So there's obviously 3 types of rocks: igneous, sedimentary, and metamorphic. Today we're going to be talking about the third kind, which are formed from other rocks that were already existing, except instead of weathering and erosion and like chemical changes like sedimentary rocks forming new rocks from pre-existing ones, this one is just heat and pressure that kind of can also cause chemical changes, like chemical reactions, that is. And it usually happens deep underground. It can happen shallower to the surface in certain environments, and I will kind of go over that further on. Now we're going on to slide 4, which is just showing you guys the rock cycle, essentially. Sedimentary rocks, igneous rocks can become sedimentary rocks through weathering and erosion, and then those can become metamorphic through heat and pressure. Igneous rocks can also become metamorphic rocks right away, like they can skip the middle step with heat and pressure. And metamorphic rocks can become igneous if they get too hot and start melting instead of just undergoing like baking change. That's a simplified chart. And now we're getting into the weeds, the how of metamorphic rocks. Obviously, I'll just go over like a little quick definition for what metamorphism actually is, or how metamorphic rocks form. Basically, metamorphic rocks form when pre-existing rocks are subjected to high heat, high pressure, and or magma contact. That does technically go into the heat category, so I didn't really include that as a separate thing in the slides, but I have it in my notes. And metamorphism can happen quickly, like at tectonic plate boundaries. That's the one that I talked about, the exception that it doesn't have to be deep underground. If it's tectonic plate boundaries, it can happen shallower, or it can happen very slowly. Usually this is what happens, like deep underground, especially for like mountain building processes, which is called orogeny. I'll probably spell it out here in the video. I don't know if I forgot to do that for the last video when I said I was going to spell something out for you guys. If I did, just remind me. I will definitely try to remember that for this video. So obviously, like I said, there's two different, like, I guess speeds it can go at. And now I'm going to show you guys slide 6, which is just showing you guys orogeny, which is mountain building. That is actually a kind of regional metamorphism. In fact, it's the regional metamorphism, essentially. So basically, in the diagram, you can see different, I guess you could say, how am I going to try to explain this? So let's say rocks have already been laid down, obviously. Sedimentation has occurred, it's become sedimentary rock, whatever, etc., right? And now, as regional metamorphism happened, it's basically squishing all these layers in between. It starts kind of crumpling it up so that they start going upward. And the thing is, the deeper that the rock is buried, the more heat and pressure it's under, so the more, like, the higher the grade of metamorphism. That's why not all of them become slate. So deeper down, as you keep going, as the heat increases and as the pressure of overlying rocks and squeezing increases, you go from slate to phyllite to schist, and then to gneiss and migmatites. Like, really heavily metamorphosed rocks are usually deeper in the mountains. And those two arrows are just showing you, like, the direction of pressure. It's going inward. That's how mountains form. That's a very simplistic explanation for how mountains form. Also, if I keep blinking, it's because I have a little bump on my eyelid. Love when that happens. Alright, so now we're going to talk about protoliths. Basically, the deciding factor for, like, what metamorphic rocks are actually composed of and how they're textured. So basically, the protoliths are just apparent rocks. Remember that metamorphic rocks do form from pre-existing igneous, sedimentary, or other metamorphic rocks. So what the rock originally was also determines the composition of new metamorphic rocks. The composition can change if the rock during metamorphism comes into contact with, like, super hot fluids that kind of introduce new minerals, if they're carrying them into that rock body. But usually the composition pretty much matches what it was originally. Protoliths can basically be shale, igneous rocks like sandstone/siltstone, like limestones and dollostones, coal. It can even be conglomerate. Conglomerates can become metaconglomerates, basically. It can be really any rock. Any rock can form a metamorphic rock under heat and pressure conditions. So protoliths vary, but they tend to be grouped by what's commonly seen later. Like, we're not going to include every single rock that could exist on the face of the planet in these ID charts, because, you know, then we would never see an end to the chart. But I'm going to go over, like, the common ones. But just know, any rock can form a metamorphic rock. Anyways, going on to slide 8 now. The agents of metamorphism, like I said, are heat and or pressure. Contact metamorphism and, like, all that stuff that has to do with that does fall under the category of heat, just so you're aware. So basically, there's two different kinds of pressure that can be involved in metamorphism. It can be confining pressure, which is just equal pressure on all sides. Basically, what I'm talking about is that as sedimentation occurs and, like, more layers of rock keep being, like, kind of deposited on top, it starts to push it down thanks to gravity, like, and the layers that were originally deposited start to go deeper and deeper and deeper, which means it starts undergoing more pressure as more stuff is added on top, and that can cause metamorphism. Then obviously there's also, I was going to say before I move on to the other kind of pressure, that kind of, like, pressure, burial and compaction, that generally speaking has equal pressure being pushed down on all parts of the rock body. So it's not like you're not going to see specific deformation on one side of the rock body and then not see it in the other if it's undergone burial metamorphism. That's that little note. And then of course there's directed stress, which is not equal in all directions. It tends to be associated with, like, mountain building processes. Remember in the diagram earlier that I showed you guys, there was arrows pointing this way. There's not really an arrow necessarily pointing up because it's not like pressure is being exerted up. The reason the layers are coming up that way is because of the pressure. It's kind of crumpling it. If you've ever tried to like if you ever have a paper, I guess I could technically show you guys this actually. For all of you who understand how this works, you're probably thinking, why is she taking so much time to explain this? Some people could be younger and have never thought of this concept, you know? Different levels of education, right? I'm trying to teach you guys something. So let's say this is like the rock layer, right? The way that directed stress works, especially for mountain building, is as pressure gets like pushed in on this kind of horizontal axis, pushing it inward, it starts to go up while some parts go deeper down. There's not necessarily any pressure coming from this direction, but those layers are still crumpling upward. That's just kind of how physics works. And then there's also not really a direction of pressure going downward unless there's also confining pressure involved. Which, it probably would be more dynamic of a metamorphism if there's like a whole different bunch of directional stresses being added. Anyway, so yeah, that's how that works. So it's not equal in all directions. It's usually associated with mountain building as rocks are being squeezed, crumpled, and stretched while tectonic plates kind of come together. So it's basically as stress-related pressure increases, metamorphism takes place, incredible heat and pressure is being pushed inward, so you start seeing metamorphism of those rock layers. Friction created by certain types of stress like shearing can also cause melt, which then causes contact metamorphism. So there's like different kinds of metamorphism can occur in the same general area at the same time. Or over different times. Like contact metamorphism could happen in a place that's already undergone regional metamorphism because of something that happens like magma rising. Just letting you guys know that. And what I mean by shearing is basically, because there's different types of like, I should say, stress that can happen. So if two plates come together, but instead of crumpling together to form mountains, they just kind of do this motion where they're sliding past each other, that causes friction, obviously, as they're bumping and grinding against each other. So basically, as this is happening, like rocks are being ground into a very fine dust type of material, and then that causes not only for melt to occur as the friction increases, rocks can melt, and then that can cause other rocks nearby to be baked, but can also create something called mylanites, which are very, very finely grained metamorphic rocks. And I think I mentioned the mylanites later as well in the slide, so don't be surprised if you see that show up again. And then, of course, the other agent of metamorphism is heat. This can occur either through the natural geothermal gradient. As you go deeper down, it just tends to get hotter, or it can occur through contact metamorphism. So this is slide number 9. So basically, generally speaking, I'm sure everyone is probably aware of this. The deeper into Earth you go, the hotter it gets. There's about an increase of 34 degrees Fahrenheit for every 100 feet down that you go. And for everyone else, that's like 1 degree Celsius for every 30 meters. Give or take. Please don't correct me on my math on that. I mean, you can correct me if you want to, actually. If you want to get into the specifics, into the weeds of geotherm, go ahead. I always recommend and would encourage further research on your own, obviously. Since I'm not your teacher, I'm allowed to say that because I'm not getting paid to teach you. Not yet, anyways. But yeah, so these temperature increases actually do jump higher and higher between levels the deeper you go. So, like, for the first, let's make like an imaginary number up. For 200 feet, right? No, 200 feet is too little. Let's say for 2,000 feet, right? Every 100 feet, it has the same temperature increase, 34, 34, 34, 34, 34. But then once it reaches a certain point, the pressure is so intense that the temperature increases start to like jump up even in like, I'm trying to find the word. It's like it escalates, the temperature increases. So then you can see a jump of like 50 degrees depending on the certain, like once you reach a certain level. Then you could see another jump of like 60 degrees because it's getting so hot because of the pressure. So I hope I explained that well enough for you guys to actually understand. As things get really hot, mineral composition changes due to the rocks being baked. And that tends to include like dehydrating of the rock as well. There is no melting though, because then the rock would become igneous, just so you're aware. If the rock is melting, it's not metamorphic, it's igneous at this point. It has to be just hot enough that it can bake and change, but not hot enough to melt. And that's the metamorphic, I guess you could say, arena, right? Area, whatever. Words are difficult. And then, of course, there's contact metamorphism, which is just what happens when hot igneous rock or magma intrudes into pre-existing rock and it bakes the surrounding rocks that don't melt along with it. And the mineral structure change occurs. You don't need high pressure for this to happen. It can occur at pretty much any layer of earth, as long as the rock layers are not melting but are in some way in contact with hot magma, it can get baked. So yeah, fluids play a role too, by the way. If there's like a lot of the more hot fluid that there is, the more that this hot fluid will move around, and then that will kind of transport things around that can cause more chemical changes in rocks. Just make note of that. Now we're going on to slide 10 so you guys can see contact metamorphism. I showed two different diagrams here. One is a more simplified version where it's basically just like a horizontal cross section. You can basically see layers of shale, like 3 layers of shale, and then there's a limestone layer, then there's a quartz sandstone layer, and then another layer of shale. Before magma intruded, this was all just very straight, obviously, but then as magma starts to kind of push its way upward, causing contact with, like, between really hot melt and, like, already cold sediment, like, sedimentary rock, the specific area that's in close contact to the... Let's see if this behaves, because the camera it stops recording randomly. I think it's because of something to do with the memory. I'm not sure. I have to get that checked, honestly. But yeah, so like I was saying, the parts of the rock bodies that are in direct contact with the magma start getting baked. So then you see the limestone layer, you start seeing marble forming along the contact points, you start seeing quartzite form along the contact points for the sandstone layer, and then you start seeing hornfels form along the shale layer that's in direct contact with the magma. So that's how that works. And then I also have like a little block diagram for contact metamorphism, which is just basically showing the same thing but bigger. So you see shale becoming hornfels, quartz sandstone becoming quartzite, and then limestone becoming marble. And the metamorphic grade does increase as it gets closer to the magma chamber. I'll explain more about metamorphic grade later, obviously. And now we're going on to slide 11. So yeah, the processes of metamorphism. I'm thinking of making future videos on certain aspects, obviously. I don't always make these notes to you guys out loud, but I do plan as I make these lesson plans. I'm like, certain topics do kind of tie in, but I don't think that I would be able to explain it in one video. I'd probably need a whole video just for that. Those topics for metamorphism would be metamorphic facies, if any of you guys are interested in that. And what that basically means is the composition of certain metamorphic rocks. It's hard to explain in a shorter version, but it's basically got to do with composition. And then of course different types of stresses that can be put on a rock, orogeny, which is mountain building, faults and folds. Those may be future videos if you guys are interested in learning more about that. But aside from that, anyways, there's different processes of metamorphism. I'm going to talk about, I would say 6, right? And I do believe that these are, the processes of metamorphism, but I'm not really sure because I'm not a metamorphic geologist. And I don't think that there's even... I don't know if there's even a position for something like that, but... Anyway, I don't specialize in metamorphism is what I'm trying to say. So there could be more that I don't know about. I'm more of a general geologist. My interest was in earthquakes, so... as I've already noted in other videos. So yeah, there's regional, contact, dynamic, hydrothermal, subduction zone, and shock metamorphism. So regional metamorphism is pretty, simple. It's caused by large-scale geologic processes, like mountain building, for example. It does involve intense pressure and heat, both play a role in this, and obviously differential stress, but that has to do with pressure. Usually this happens along convergent boundaries. And I do think I'm going to make a future video on, the different types of tectonic plate boundaries. I think I've mentioned that in another video. If not, you guys are aware that I am planning that. Because there's divergent. There's, divergent boundaries just basically means that the crust is pulling away. Because the plates are pulling away from each other. Convergent means that the, crust is kind of getting crumpled up because the plates are coming together. And the third type, I can't remember what it's called, but it's the one that does the sliding motion. That it doesn't collide or pull away, but it does come into contact and cause friction. The resulting rocks of regional metamorphism tend to be deformed because there's a lot of crumpling and stuff like that, and you usually see faults, fractures, and cleavage when it comes to rocks are planes of weakness that the rock will break more easily along those planes, and that has to do with composition and mineral shape and size, etc. Usually regional metamorphism has a larger area of effect, hence the name. It usually produces foliated rocks. Metamorphosed rocks do tend to, in this category of regional metamorphism, do tend to form roots of mountain chains and are only exposed as weathering and erosion of the overlying layers occurs. So basically, as the upper layers are kind of sandblasted away or washed away or whatever by weathering and erosional forces, then you start to see these cool mountain spines start to emerge, and you can see all these cool highly metamorphosed rocks. And they can even serve as indicators of ancient mountains in the flattest plains. And you could not imagine that a mountain was ever there. If you find metamorphic rocks in the ground there was probably an ancient mountain there once. It just got eroded away over time. We are a pretty new species on this planet. Do remember that. And then, of course, there's contact metamorphism, which I explained earlier. It's just basically what happens when really hot magma comes or other fluids come into contact with already pre-existing rock, and that causes them to metamorphose because of intense heat. So it's temperature based. It's not really a pressure thing. Pressure doesn't play a role in this. It has a small area of effect, usually up to 10 kilometers. I don't know what that would be in American measurement. I'm sorry, I didn't think to even remotely look into that. I'm used to doing things in meters and kilometers and Celsius and all that stuff now because of my science classes. So I'm sorry. I've kind of been converted over to the way that the rest of the world does it, but I'm sure it's not going to be hard to look that up. Anyways, like I was saying, contact metamorphism, you see a lot more non-foliated rocks emerge from that. And then, of course, and we're still on slide 12, fortunately, for dynamic metamorphism. You will see this either in mountain building events or fault zone tectonics, which I may also make a future video on that, just so you guys are aware. In terms of orogenic, cause of metamorphism, it's basically huge forces of pressure and heat tend to bend, fold, crush, flatten, and shear rocks. It's like God is playing with very hard Play-Doh, so you'll see a lot of dynamic metamorphism there. And what I mean by dynamic metamorphism, I just basically means that I'm just basically saying there's a lot going on. There's stress, there's confining pressure going on, there's probably high heat going on as well, there's fluids. It's just everything is happening at once. So yeah, in fault zone you tend to see that a lot, which is just basically high differential shear stress crushing and grinding rock, resulting in deformed and very fine-grained rocks like mylanites. I think I mentioned that earlier. I know I mentioned that earlier. My memory's not that bad. It's not just shear stress involved, like I said, there's a lot going on for dynamic metamorphism. And now we're moving on to slide 13, so I can show you guys a diagram. This is a fault zone. This is the one where the blocks are sliding against each other, the one whose name I can't remember. So basically that is showing you the shear zone. If you zoom in to where it's sliding against each other, you can see the rock. The normal rock has a specific mineral structure. It shows you kind of a little zoom in. But as the rocks keep grinding and grinding and grinding and grinding, they start to become so fine particles that they kind of start lining up in a specific way as well. And then you got your mylanites. It's very tiny grains. It's the same composition, just very, very finely grounded. It's like the difference between powdered sugar and granulated sugar, Granulated sugar is just coarser grains of sugar, it's not been ground down much, if at all. And then powdered sugar has basically been ground down to extremely fine, tiny, teeny tiny little specks of sugar. And that's why you can usually see little explosions of sugar if you pour it too fast in something with powdered sugar, but you don't really see that with granulated sugar. It's kind of like that difference, but with rocks. And I'm sorry for the sugar reference for those of you guys who are not the least bit interested in that. I am also a baker, so that made the most sense to me to explain it that way. And now moving on to slide 14. So on to the next process of metamorphism, which is hydrothermal. So basically this is another temperature based one, and it's super hot mineral rich water circulating through Earth's crust, causing surrounding rock to metamorphose. You obviously will see this a lot more in the ocean. You specifically see it a lot in mid-ocean ridges, which is a type of divergent boundary, so like the crust is being pulled apart. So yeah, if you ever hear people panicking about the Earth pulling apart and magma coming up, that is normal for Earth. Don't let anyone freak you out into thinking that that's like the world is coming apart. That's just been happening for millions of years. So yeah, basically the plates are coming apart, and as they do, hot magma is rising and coming into contact with cold seawater that has other minerals. So that causes metamorphism of the igneous rock that's just newly formed along that little ridge line. And it can also introduce like salt crystals and stuff to kind of change the composition. So then of course there's also subduction zone metamorphism, which is just very high pressure. Like it's a very, very high pressure type of metamorphism. Temperature doesn't really play a role in this. Basically, as oceanic plates sink into the mantle, high pressure minerals are forming. It's a chemical thing. And then, of course, there's shock or impact metamorphism, which is what happens when meteorites or like other, extraterrestrial objects slam into the Earth. It's a high temperature and high pressure thing, just like regional metamorphism. Basically, extreme shock waves create microscopic physical or chemical changes in rocks, and it can produce very high pressure minerals, like shocked quartz, for example, is a really cool example of what is it called? Shock metamorphism. Now, on slide 15, it actually shows you a little diagram of of an impact event. As the projectile kind of comes into contact, basically it starts pushing up a lot of the layers of the Earth because, it's displacing it. So the layers are kind of going like this around this big thing in the center. The thing it comes into direct contact with, it melts because of how hot it is. But beneath that, there's a layer where you have shock metamorphism, because it's in contact with the melt, but it's not directly being heated by the projectile. And then, of course, you got fracturing and brecciation in, like, lower layers, which basically just means things are, like, being torn apart. Very sharp rocks are being produced by this event. That's what we're interested in on the left side of the diagram. I'm not really that interested in the right side. That's just talking about ejecta and slow pass and all that stuff. If you guys want to look into that, you can. Of course, and I think I have a few slides here, slides 16 to 18, where I just show you samples of shocked quartz. So that's a sample of shocked quartz. That's not my hand, that's some random person's hand. I found this picture online, obviously. You see that little part, like the white part right there? That's the shocked part. Like the transparent part is normal quartz. The part in the center is the shocked quartz part. And then slide 17, it shows two different samples of shocked quartz again. You can kind of see like it has like a similar sort of like weird line sort of thing going on here. And it also has significant discoloration. So usually quartz is naturally more clear unless there's an impurity. Like that's how you get your rose quartz and stuff like that. And then also unless an event introduces other impurities or extreme heat and pressure, like for shocked quartz. And then slide 18 is just a photo micrograph from like a quartz sample from the Chesapeake Bay impact crater. That literally shows you just how like most of the changes that are occurring are on a microscopic scale because it's happening directly to the structure, the actual quartz. So that's why it looks so cool and like multicolored there. Quartz samples don't usually look that awesome, honestly. And now we're moving on to slide 19, which is grades of metamorphism. So basically, as I mentioned before, there's this concept called metamorphic grade. So what that is basically just referring to is that, what I'm basically trying to say is there's a scale, right? Not everything that's metamorphosed has been metamorphosed to the same level. So as temperature and pressure increases, rocks go through increasing levels of metamorphism as temperature and pressure increase. So, like, it has to do with how much temperature, like, how high the temperature is, how much pressure is present. That's how high the metamorphism is happening. And this scale is called prograde metamorphism. So, basically, the low-grade metamorphism falls in the scale of, like, 392 to 608 degrees Fahrenheit, or 200 to 320 degrees Celsius. It's relatively low pressure present. It's not really like a low grade metamorphism doesn't necessarily require high pressure to become active, obviously. It tends to produce metamorphic rocks with like higher percentages of hydrous minerals, which just means minerals abundant in like water in the structure. As your metamorphic grade increases, you will start seeing chemical reactions that cause those minerals to begin breaking down and changing to less hydrous minerals. And that's why I said rocks are dehydrated as metamorphic grade increases earlier. Because you start losing water, it's basically being baked out. High grade metamorphism basically occurs in any temperature range above 320 degrees Celsius or 608 degrees Fahrenheit. And it also, you see high pressure there, and you see a massive water loss in these rocks. And so with that basic understanding, we're moving on to texture now, which is slide 20. So basically, foliation is not a thing that has to occur in every metamorphic rock. It's a really cool thing that occurs, but the only way that it does occur is if the right conditions are met. So basically, foliation just refers to like the parallel alignment of mineral grains in a rock due to pressure and heat application, forming like bands of different composition that kind of tend to, because the same compositional parts in a rock tend to kind of stick together as heat and pressure is applied. And that's why you'll start seeing color banding as these things kind of align with each other. You won't see this in certain rocks because they just don't have the right minerals present that will allow for foliation to occur. So basically, the mineral grains have to be flat and or elongate in order for this to happen. It doesn't matter how much you squeeze other rocks that don't have these grains, they just won't align because they just don't have the capacity to do that. And those rocks are non-foliated. So basically, as metamorphism occurs, rocks split along cleavage lines, which, like I said, are planes of weakness, parallel to mineral alignment, and that's how the color banding is formed. As the rock is splitting along these planes of weakness that have to do with the actual mineral composition, it's a very mineral composition heavy topic explaining cleavage. If you guys are interested in that, I will try to explain it in a future video better than this. But basically, it's a trait of the actual mineral structure, whether or not there's specific cleavage. And so as rocks metamorphose, it'll split along cleavage lines, and that's how color bands form. But if you don't have the right grains, you're not going to see foliation. I know I'm beating a dead horse by explaining it over and over, but I'm trying to make sure that at least somebody understands what I'm talking about. The right grains, the right minerals for foliation to occur are actually micas and chlorides. Those are just minerals with like sheet crystal structures. And if you want, I can do a separate video on like the types of bonds that can form between atoms in crystals to explain why their structure turns out certain ways. But aside from that, aside from the whole video that I might do on it, sheet crystals basically, like, they could have like a whole little line of crystals aligned and then another line of crystals aligned, and then there's like a very weak bond between those two sheets that kind of keeps it together. And that's how like sheet crystals like micas and chloride form. And they're called phyllosilicates for anyone who's interested. So the ones that have the right minerals, like the rocks that have those minerals in abundance, tend to be shale, siltstone, and felsic igneous rocks tend to have those in abundance as well. Things like marble do not have these types of grains, so they don't tend to foliate when they metamorphose. Something also like quartz sandstone won't have micas present anymore because they all have been weathered out by this point, and that's why they tend to form quartzite. If they have, because sandstones that have micas still present will tend to metamorphose more into gneisses and stuff like that. So yeah, hopefully that makes sense to you guys. Yeah, now we're moving on to slide 21 for grades of foliation, because just like in terms of like grades of metamorphism, like how metamorphism doesn't all happen the same at every level, there's levels to this. There's levels to foliation as well. Foliation can increase in intensity as metamorphism increases in intensity, as you can imagine. Usually this happens deep underground as mountains form. You will not see levels of foliation occurring in places where there's not time for this to happen, for metamorphic grade to increase. So low grade metamorphism, you'll usually see slate, things like that. Slate is like very thin, like layers, essentially plates. They can break into plates, the rocks. because of how perfect the cleavage is. And then phyllite obviously comes next. That's a low to medium grade metamorphism. And it's very satiny and glossy due to the growth of platy minerals over time. It can also be quite reflective in some samples. Then there's medium grade metamorphism, which is schist. That's where you'll see that. It's higher heat and pressure than slate and phyllite. Many of the minerals are altered into flakes, which can kind of come off quite easily, and they're often enfolded and crumpled due to more intense pressure being applied, obviously. And they tend to have names that have to do with the main composition of the rock. For example, you could have a biotype mica schist, a hornblende schist, etc. And then, of course, there's high-grade metamorphism, which produces gneiss. These are the most intense heat and pressure applications that you can imagine. That's how gneiss is formed. Basically, you see distinct banding separating different compositions in the rock. Gneisses mostly have the same composition as granite, but you can also have diorite gneisses, which are mostly the same composition as diorite. They're either formed directly from igneous rocks like granite or diorite, or they form from sandstone or shale that still have micas present, or other phyllosilicates that can cause foliation. They tend to be composed of feldspars, micas, quartz, etc. And then obviously, now we're going to move on to slide 22 so you guys can see samples. I'm going to show you samples of every kind of foliation that you can see. Wow, that was redundant. You can tell I'm tired. So yeah, slide 22, you see a little sample of slate. You can see that you can almost imagine putting your fingers between those two different layers and just kind of popping it apart. And so then there's phyllite on slide 23, which is very reflective, as I said, very satiny, glossy, two different samples, kind of have the same general look to it. The second photo shows a far more reflective sample than the first one. And then slide 24, you see a schist. It looks like flakes. Like, by the way, that rock probably is very crumbly when you hold it, and you could probably take the flakes off with your fingernails. They are not very tough at all. And then slide 25 shows you a gneiss. That distinct color banding is due to intense pressure and heat. Basically, all those minerals have distinct cleavage, and they have just aligned along it as they've been fracturing and stuff. And then slide 26, we're going on to the non-foliated metamorphic rocks, which is just basically everyone else. You have your quartzites, your marbles, your metaconglomerates, your anthracites, serpentinites, and hornfells. Quartzite forms from quartz sandstone, as you can imagine, that doesn't have any micas or other phyllosilicates present. Marble forms from dolostone or limestone because they just don't have those kinds of minerals. Metaconglomerates can form from quartz-rich conglomerates, where everything else has been basically weathered out. Anthracite forms from bituminous coal. Anthracite coal is actually apparently native to PA. Like, there's a lot of it here. I don't know if it's only in PA. I'm not saying it's endemic to PA, but it is native to here. Sure, other Pennsylvanians know this. And that's basically just metamorphosed coal. And then there's serpentinite, which can come from mafic or ultramafic igneous rocks directly. Like, basically, those very mafic rocks have been metamorphosed without going through a sedimentary phase. And then hornfells can come from literally any other rock, as I mentioned before. And so, slide 27, you see examples of quartzite. Just admire the samples for a couple seconds, guys, because they look pretty cool, honestly. I wish I had a sample of this. I do believe no, the last time I actually saw a sample was in my geology class, unfortunately for me. And then, of course, there's a marble sample on on slide 28. Slide 29, you see a metaconglomerate. That's really cool. I think that's been polished, because they're not usually that smooth, but you can kind of see all the big, like the way the conglomerate has basically been metamorphosed, so it looks, because normal sedimentary conglomerates do not look that nice. But you can see how the rock grains have been stretched due to pressure and, like, differential stresses and heat and all that stuff. And then slide 30 shows anthracite coal. Slide 31 shows serpentinite samples. The characteristic darkish greenish hue, you're probably looking at serpentinite, because that usually means that it's very heavy in mafic minerals. And then, of course, slide 32 shows you hornfels samples, which, like I said, can come from any rock. And then other features of note are grain size and hardness. Grain sizes for metamorphic rocks can range from very fine to coarse grain. You're not going to have many massive grains, except for like metaconglomerates. Most of it tends to be coarse or smaller. Very fine, it falls in the slate category. In the fine category falls phyllite, anthracite, hornfels, and serpentinite. Medium to coarse, you see your schists, your gneisses, your marbles, and your quartzite. And of course, coarse itself is like metaconglomerates. And in terms of hardness, this matters more for non-foliated rocks because foliated rocks are way easier to distinguish by just looking at them. Looking at the grade of foliation and metamorphism that's occurred, you can pretty much identify them a lot faster. But for non-foliated rocks, it can be a little more difficult, especially if you guys notice that quartzite and marble can look pretty similar. Quartzite tends to be much harder than marble. It's around a 7 on the Mohs hardness scale, and I believe I've talked about that before with my rock ID videos. And the reason it's so hard is because of the high quartz content. Obviously, quartz is a very hard mineral. And then there's marble, which is around like a 3 in hardness. You can probably scratch it pretty easily with like a nail, not your nail, a steel nail, like a metal nail, or like, you know, it probably isn't going to scratch glass, something like that. Also, it will fizz with acid. That's usually how you can tell the difference between quartzite and marble, if everything else is failing you. And then anthracite is around like a 3 in terms of hardness, and you also see a very low specific gravity. And what that basically means in layman's term is that it's pretty light for how big the sample is. Like, you expect it to be heavier, but it's surprisingly light. That might point you to anthracite, especially if it's very shiny, because anthracite is extremely shiny in comparison to bituminous coal. And so then the rest of the slides are basically just showing you like different ID charts, like I said, like the different possibilities for ID chart. Slide 34 shows one that's separated by texture and then by further characteristics. And you guys can take your time, pause, or look at the pictures if you want. You don't have to go at the pace of my editor. And then slide 35 shows a classification chart that's separated by texture and then by protolith, which is like the parent rock. Slide 36 shows a classification chart that also includes grain size, and it has texture, obviously, the protoliths, and it even has like little pictures for what you can kind of expect to see in the texture. And slide 37 shows classification that's first separated by texture and then by protolith, and it goes from grades of foliation increasing down to like possibly non-foliated, or possibly foliated, that is, and then all the non-foliated rocks. And you also see photos of each type of rock on the right hand side. And then slide 38 has a really cool classification chart that not only includes composition and type of metamorphism and like, you know, that the rock underwent, but also like grain size and texture are really big characteristics for this. And it even shows you map symbols. So basically, when you're looking at geologic maps, different rock units are separated by commonly accepted symbols so geologists kind of know what they're looking at. Like sandstone tends to have a very specific symbol, and then like shale has a very specific symbol that is usually commonly followed. I think the USGS has like resources for you guys to look at if you're curious. This classification chart basically shows you the map symbols for these kinds of rocks, like for these kinds of metamorphic rock. And generally speaking, metamorphic rock, if it's like only one metamorphic body and most of the rocks are sedimentary or igneous or whatever, or actually metamorphic and igneous rocks are both considered crystalline. So they tend to have like the same types of map symbols when in comparison to like sedimentary rocks that tend to have a wider range of map symbols. But in this classification charts case, it actually shows you the different symbols for each type of metamorphic rock. I imagine that would be more useful if you're looking at a highly metamorphosed region, like for example a mountain that you're looking at different layers. And so yeah, that's pretty much it, guys, for today. So basically, I'm probably planning future videos on like metamorphic facies, different types of stresses, orogeny, faults and folds, fault zone tectonics, maybe crystal bonds. If any true nerds are interested, do let me know. for homework for today, you guys can just look up photos of mountain chains. You can even check on maps or like, you know, Google or whatever you want to refer to how long the largest chains are in the world, because this can show you just how massive regional metamorphism can get. Like, there are some mountain chains that literally stretch entire, like, for example, the Appalachians, huge mountain chain. That basically shows you that the regional metamorphism was going on, like, it was such a large area. It was like the whole East Coast is basically just pressing in on itself. So yeah, basically just look into stuff that you're interested in, like the stuff that I mentioned, mountain chains, and look up photos and stuff like that of big mountains for, let's, you know, keep it PG. There might be kids watching this. And that'll be all for today. I'm sorry if I kind of sped through it. My eye has been bugging me this whole video, man. And I'm also kind of tired and hungry, and dinner has been ready for like 20 minutes. So at this point, I am logging out. If you guys have any questions, obviously, if you want to see future videos on certain topics that I didn't mention making a future video on, do let me know. If there are certain topics that you do not want to see a video on, that you can spare me from making a video on, also let me know. And, you know, any other questions, comments, concerns, leave them in the comments below. And I'll see you guys another day. Bye, and stay curious. Actually, guys, we're not going to make the same mistake we did last time. Last time I forgot to show you guys the samples that I have in my collection of sedimentary rocks. I'm not going to do that again. So, I do have a few samples here. Some are uncertain because I can't remember what I identified them as. Honestly, I'm going to be so for real with you. I don't remember half of the rocks that I've ID'd now that I've already ID'd them, which might be a problem. I might have to go through and kind of note, like, you know, label them according to what IDs I gave them in my other videos. But for now, whatever. This is a gneiss, if I'm not mistaken. Unless it's just a sedimentary rock with a lot of quartz veins. Because it could also be that. But this is kind of what you would expect in terms of appearance of a gneiss, I should say. Look at that color banding. Super cool. This might be another example of a metamorphic rock. Not entirely sure, honestly. It's pretty hard to tell. And probably harder to tell with the really bad lighting. Hold on. Hold on. There we go. Anyway. And then here are two different samples of schist. I do not have an example of phyllite or slate. I thought I did, but I don't. You see how those flakes are like, they're very shiny flakes. And yeah, I can actually just scratch them right off with my nail. Maybe not, actually. They're not that weak, actually. But yeah, so this one is kind of not cooperating with the little test that I'm trying to do on it, but this is definitely a schist. And this guy is a schist, and it does scratch off easily. See? I'm not sticking my middle finger out at you, I am just trying to show you the flake on my finger. And that came off pretty easily with very little pressure, so there's another little schist right there. Very crumbly, very